Welcome everybody to today's Python meetup. I have to admit that this is the first Python meetup that I'm attending. I was organizer of Ruby meetup ages ago, and I had to be more present in that community than this, and I hope that you guys understand. Yeah, without further ado, I would like to start this talk. The main point of this talk is essentially a bit of a joke. The point is that as engineers, we like to explore, or we like to have fun with technology, and those kind of those ways of doing things usually lead to a lot of experimentation, and that usually can be seen as over-engineering in certain fields. So this is one of those over-engineering stories. It could be seen like that, or it could be just seen as exploring new technology and looking into few things of how modern distributed systems are built. And yeah, I'm going to start with this joke that you might have seen. It's essentially a story of over-engineering, and it says that over-engineering is only good for a very handful of problems, and usually you should not over-engineer things. And as engineers, we should always strive to a solution that's only needed for a given problem. But yes. The story of this project actually starts in our co-working space, in our co-working group, or our team. Me, Andraž, and also Yura, I can say we belong to this co-working group called Gigatrons, and it's a place where a couple of technology enthusiasts, let's say, work together. And the story with this project starts with this co-working group in a morning coffee, when we were discussing, among other things, let's say, that the wireless is a very interesting technology, and despite its evolution and age, all that stuff, it's still possible to extract quite valuable information merely by observing what's happening on the network. And that could be achieved by usage of pretty standard equipment that usually lies around. And out of that discussion, we then started debating more and more with Andraž how it would be possible to capture all this data passively, and what kind of information could be extracted out of that information, and if that information could be used for security researchers or whoever is interested in that topic. And out of these coffees and discussions, this project was born, and this is the story essentially of that. And yeah, let's start that. I invited Andraž to this talk because he was also very helpful with this project, and I'm going to invite him to share us a bit more technical information about how wireless works, and what kind of data is actually available, and what kind of data could be sniffed, and what does that data actually mean. And yeah, I'm going to give him a couple of minutes to give you a bit of insight in that. And I highly recommend that you pay close attention, because it's quite important for the talk in general. So, Andraž, you ready?
Sure. Hello, also from my side. So basically, if I add to this conversation that started, like I introduced Oto, that with simple capturing what's happening in our surrounding, I can quickly get enough information to track specific device, or to track the specific device where this device was before, and so on. And Oto was like, so no, not possible. And that was original challenge. And for the let's say basic stuff related to wireless, this project was focusing on wireless, we know, like wireless, Ethernet wireless, so devices that are connected over the wireless certified by the Wireless Alliance, meaning what we right now known as connecting to access points and put together mobile devices, IoT devices, and so on. So we're not focusing on wireless, meaning Zigbees, LoRaWANs, and so on. So basically wireless between devices and access points. And I think the most important stuff that sort of you need to know that is hidden from the end user is the design. So basically on one side you have the station, which means this is the end device. It can be the smartphone, it can be the tablet, your laptop, and so on, with antenna that is communicating in this radio frequency medium. And on the other side, you have the access point that basically is same device as the station, but it also has a connectivity to the other net, meaning it's sort of a portal connecting wireless device to the other part of infrastructure. And this kind of APs are like for consumers are known as the routers. Usually in enterprise world, AP does not do any routing. It's more of a hub for those who are more familiar with networking. So basically what's happening all the time is those devices are communicating between each other, and because there's no full duplex, so once one device is transmitting, other needs to listen, and so on. So to make sure that this protocol actually work, there are specific kind of traffic going on called management frames. So this is the frames that are not visible to users, but are visible to devices, to make sure that they are capable of parameters set for specific network to operate. So one interesting part that is happening here is the so-called beacon management frames. And this is something that is transmitted or broadcasted from AP. So AP announces his visibility or his presence in the surrounding, and is saying like, this is my SSID, sort of logical name of the network, announces its capabilities, the frame rates, and so on. And on the other hand, the stations, so your end devices, are listening to those beacons. And this is when you, let's say, open your laptop and select the wireless, enable wireless, you'll see the wireless networks. This is basically on collecting all those beacons and displaying you the networks. And keep in mind that by default, those for each SSID, there's a beacon is sent out every 100 milliseconds. So at least 10 beacons per second. This is one part. And the other part that is interesting in this management traffic is request probes and request response, so probe response. So once station is aware of presence of access point, it tries to connect to it. So he sends out the probe, the request, and the access point responds with probe response. And then there's a whole procedure that happens that includes also the security and so on. But for this part, we're sort of interested in collecting enough probe requests to see what are actually device scanning, and based on this, sort of have a good visibility where these stations actually moving, or in which networks have been in past, because you might see that if you already been in one network and your device was already connected, by default it's tried to reconnect once it sees same network. And same goes for devices that are just trying to connect to network, even though the network is not present at that location. And by collecting all those probe requests, you can actually see where this device was in past. So this is the quick overview. I really don't want to go into details, but for the design, everything is open. So this protocol to actually work, you actually see the network names, you see the MAC addresses of devices connecting, and so on. So that's this part.
Okay, thank you, Andraž, for this. So the bottom line here is that what we'll be showing and demonstrating is the way that wireless network of this kind works. There is nothing strange or not anything that we did to abuse anything in the system. It's just how networks and the software around it works today. So that's, I think, an important thing we should also mention. So you can replicate whatever we did here on your network at home, or you can play around with this, I think. Do you want to add anything to that? No? Okay, cool. So yeah, as you see, we started discussions around this and in these directions. I got familiar with this kind of problem, and out of that, we then discussed what and how could you prototype of how could you actually get the data and what can you actually do. And the idea is pretty simple. So capture all the data that you can around a specific location, and then visualize that data in some kind of way. And that's essentially the whole idea of this project. And this project was then a bit rehashed and a bit rethought, and it got this name called Oracle Peak. And the name Oracle Peak originates from this attack called the Oracle attack, which is an attack where you introduce some kind of entity that observes activity in certain area. And because it has this passive role and passively observes, it can then use that data in order to facilitate other attacks or be used in some other way. So out of that Oracle attack name, out of that attack, this project then got the name Oracle Peak, as essentially as a technology or tooling that actually observes and has this knowledge. So that's why I'm going to use that project name. So the pad that I envisioned for this project was essentially first in 4 steps. So build some kind of a device that will do this kind of capturing, then capture the actual data, process that data in some kind of way that you can do some kind of research on top of it, and then visualize the results. And that's, I think, pretty standard way of how everybody would approach this, right? But, then you realize that that's like really traditional, really boring approach to how you should tackle your hobby projects or your side projects. And it was just not enough to get things going. So we introduced few more challenges and few more, let's say, roadblocks in the way. And we bumped that plan, let's say, to another level. So instead of building just a single device, we decided that we're gonna build, multiple devices. We decided that we're gonna build multiple devices, that we're gonna capture all the data. We're gonna capture all that data in real time, and that we're gonna build this thing in a way that processing can be done essentially in any kind of backend storage then. And the visualization itself should not be just purely, fetching or CSV or whatever, but it should be something in real time. That means that it should have as little latency as possible. And all these things should be done in a way that, these probes that we actually capture are so valuable that we should not lose any, meaning that the whole system should be resilient and distributed in a way that loss is just not acceptable. And the purpose of this is also to explore what's cutting edge on this front, and what could be used to build this thing rapidly, and obviously keep having fun. So essentially, we kind of like bumped the goal a bit higher. So the next step then is to build a device. And obviously you start with one, but then you ramp it up. And device, well, the first prototype was essentially this thing. So this is Wi-Fi Pineapple Nano, which is essentially an embedded device that you can plug into your USB port. And then it has some kind of user interface, which you can use, or you can use just SSH into it, and you can use it from there. But what you see on your screen is a tool called AirDump, which is a tool that's part of the AirCrack suite. It's a part of the tooling that's used for Wi-Fi penetration testing. Is that correct? Essentially, it's a tool set that you can use in order to explore or hack wireless networks. And I needed to pay a bit more attention to what's happening on the screen. So on top you have the BSS ID, and then you have another BSS ID on bottom. So essentially the screen is split in two. On top of your screen, you have the base station, the access points that were found. And on the bottom of the screen, you have probes that are set out. So you have the station, and you have the device that's trying to connect to the station. And in some cases, you will see that device is already associated with particular access point, or in some cases it's not. So something like here, you can see that some device is trying to connect to wireless, but that wireless doesn't exist. And in some cases, you'll see their number of frames is quite high, which means that there is a chance that that access point and that device are actually connected together. So this is essentially the data that you can get. This is essentially what you can now use on your machine. You need to turn your wireless card in the wireless monitoring mode. And if that card is also supported by the toolset, you can then monitor your environment. It's pretty simple. But like I said, this was not enough. We started with that, and you can see that this thing actually, it's good enough that you can quickly prototype. It's good enough that you can capture some of the data. It has OpenVRT, which is essentially a system that you can use for this kind of experimentation. It has also low power consumption, but on the opposite side, it's a pretty limited embedded device with specific MIPS architecture and pretty limited antenna and pretty limited bit outdated tooling, which means that any kind of advanced experimentation of this device would be not possible, especially at the scale that we want to do this kind of prototypes. So that was the first device. And then this was the second prototype. So you can see on top of this, this thing, you have a Wi-Fi pineapple device. And then you have in the middle of the sandwich, you have the Raspberry Pi. And on the bottom, you have additional power source so that the antenna has enough power to actually provide this data. And this was essentially the second version of prototype. So in this case, the software was still running on the Raspberry Pi, on Wi-Fi pineapple, but the actual processing was then moved to Raspberry Pi, where you have all the Raspberry Pi infrastructure available, where you can also run a bit more complicated software. So out of that, we somehow decided that that's even not as far as we can take this. So we upgraded that even further. So we got this antenna, which is from Alpha Networks, which is a very popular device for this kind of things. And yeah, from this antenna, we then built more sophisticated tooling. You can see that now all the processing is moved to Raspberry Pis, and from there on, it just keeps going. A very interesting point perhaps would be that here we started using more sophisticated, more powerful, and more long-range antennas. But this kind of thing will work also on pretty much any kind of wireless card, as long as it's supported, like I said, in the tooling, and as long as it can be put into monitoring mode. So if you plan on doing any kind of things like this, I suggest that you make sure that that you check that it's actually feasible. And yeah, then the antenna just got bigger and bigger, and more devices were added to this stack. And even that was a bit boring, so we decided to also add GPS modules to these devices. So devices now also have wireless antennas plus GPS modules, which means that they are now able to capture GPS data as long as wireless. So that means that that's also possible. And yeah, obviously this is done in this special time, so it's fun should always also be shared. And I have to say that I had some helpers with hardware, and yeah, with some help and with additional devices. Now for this project, there are now four custom-made devices. Two of them are all Raspberry Pis, one more modern Raspberry Pi volume 4, and there is also one Intel NUC, which is essentially a desktop laptop. And the system was designed so that essentially we can add as many locations and as many devices as we want. And the software was also adjusted so it can run on different architectures and different operating systems. Currently, this stuff runs on 2 physical locations here in my home, and different locations inside my house. And it also runs at the Gigatron's co-working space where the coffee that I mentioned earlier has started. So now you see that we have this kind of devices, they're ramped up and they're ready to be used. Now I'm going to move more to the capturing side of the data. So I'm going to talk more about the core concepts that were used for building this thing. So the core concept. Sorry. Sorry. Yeah, I got bombed. Yeah, so the core concept is there are 3 core concepts that were used for building this thing. First is event streaming. So all the things that were built are built around event streaming concepts, which means that the devices generate events, and these events are then propagated across the tooling to the end where the processing is actually happening. And everything was built with resilience in mind, which means that if the device loses power, if it loses network, if part of the device is down, let's say that some process dies or whatever, it's fully acceptable, and the software is built in a way that it can recover and it will continue processing once the network is back up and once the thing becomes available. Now, this is done not just on agents, this is also done on backend processing, which I'll demonstrate and talk more about later. But the idea is that, again, we should not lose any data, and we should be able to operate no matter what. And the other concept is that it was built in a way that deployment of new agents is pretty rapid, which means that if I decide to patch some software, some of this agent software, it could quite easily and rapidly be distributed on these devices. So yeah, these are the main concepts. So I'm going to talk a bit more about what's event streaming. So event streaming is essentially a way of describing business requirements or the world through events. So whatever is happening in your domain can usually be described in events. So you bought something, you visited something, something has appeared, somebody made a purchase. So all these business events that happen are captured, and then they are emitted into usually a broker. And these events can then be used to generate a state. So that means that you accumulate events, and at some point you decided, I want to sum up what these events mean, and that's usually then the representation of your state. In our case, that means that these devices are sending these events. So what you see on the screen is actual output that's coming from these devices. You can see that here we have some JSON, it has some timestamps, it has some specific tags, and based then on particular event, it has some different payload. But usually it's pretty trivial and pretty easy to understand what these events are. And these events, what's really important with these events is that they have a timestamp and that they are immutable and they are never changed. So when you create them, when you store them, they're always there. And then depending on the business case, you decide at what point do you want to either discard these events, or do you want to keep them or compress them or whatever. So this becomes really important. For example, when we have 4 devices, but if you have 10,000 devices, there's going to be a lot of data and a lot of events. So you better have some kind of strategy how long you want to keep these events in your storage. The other advantage with the event streaming is that these events are usually simple, and you can usually, based on your domain, partition them, which means that you can have, I don't know, events that happen in Slovenian data cluster, events that happen in American cluster, or whatever kind of domain you're running in. You can also distribute them, and that can essentially help increase the throughput of your system. And the other advantage is, like I said earlier, events the state out of the events can be either built from the beginning of this event stream or from the end of this stream. And usually when you introduce the concept of event streaming to people, they're always thinking like, but how I'm going to introduce mutations to the system. The solution to that is usually describing mutation as a change. So that's also another event. So in theory and in practice, most of business cases could be described through event streaming, and that's essentially the core idea here. So out of event streaming, you usually come to a conclusion that how are you gonna actually pipeline the system together. So here I have two sketches. On the left side is a sketch of how your architecture very likely looks like if you haven't introduced any kind of event streaming or any kind of event system to your stack. So you usually have this kind of silos of data lying around. So it might be Elasticsearch or Cassandra or Postgres or whatever. And then you also have your own analytical stack that might be specific to your case. And the idea with event stream or streaming platforms is that you put a broker, in our case Kafka, in the heart of your architecture, and then you capture events that happen across your platform, and then you emit those events to a broker, and based on the demand, you can then also emit those events further to other components. So that means that, for example, apps can generate events that go directly to Kafka, or they can generate events directly to, let's say, Postgres, where your currently existing business logic might live. And then you can extract the events out of the database, for example, again, into the streaming backend, and from there, you can do whatever you want with them. So the idea is that this component is in the heart of your system, and then you connect to it based on your use case. There's a lot of advantages to this architectures, and if you want to learn more, I have some links in the end, or I can give more details. But for this is going to be it for now. So I'm going to focus now a bit more on the agent. So this is the software that's actually running on these devices. The device is called Oracle Peak Agent. It's currently packaged as a Docker container built for different architectures. On these devices, you have two daemons. One is called BetterCap, which is essentially a Go binary that's extracting this data that's very similar to what you saw earlier in one of those recordings. And you have GPSD, which is a daemon that's capturing the information from GPS module. The agent then emits these events to MQTT broker. MQTT is essentially a service that could be used for bidirectional communication between broker and client. And the big advantage of MQTT is that it has really low latency, and that it has very different strategies based on your use case. So you can have a strategy where events are just fire hosing the system with events, and they don't care if they are delivered or not. Or you can have a pretty rigid delivery contract where you want these events to be written for sure. And MQTT is, if you explore any kind of IoT devices today, I think the de facto standard for any kind of IoT tooling. And it's, in essence, it's pretty simple. And MQTT, for example, was built when they were trying to operate, I think, oil rigs through the satellites. So it's really low latency and really straightforward implementation. And that's why it's so very popular with embedded devices or devices that operate on low power. Now, when you run this client, usually the output looks like this. It's not that impressive. What is more impressive or has here is this final line that you can see here, is this resiliency. Because this thing is written in Scala and Akka. It has few advantages. One of those advantages is that it knows how to back off for when certain data streams are not available, and it could then react to those changes, which means that, for example, here there is simulation that BetterCap was down, and the agent essentially waits for it to be available. When it's available, it will start consuming and emitting data forward. If, for example, MQTT broker is down, these events will be accumulated. When it comes up again, it will be emitted from the log. So there is some kind of resiliency happening on the agent that makes things more robust. And what you see now on your screen is essentially MQTT Explorer, which is a tool that you can use to look what's happening on these inside MQTT broker on your specific topics. So if you see here, it's essentially a tree structure. And here I'm browsing through two locations. You have location Gigatrons, location 1, and you can see here that when the screen is flashing, that means that these events are emitted in real time through the broker. So whenever the screen flashes, the device actually sends the data through. I have this beautiful snippet of the agent code, which is not that impressive. The impressive piece of the code is if you look here on your bottom left, where formatter off and formatter on is written, you might see some really interesting like arrows. That is essentially the definition of the graph that's happening on device. So you can see that the session information is flowing from left to right through broadcasting, then something merging is happening, etc. So more or less, this and a couple more files is the whole software. It's running this thing on the agent, and it's pretty error prone, pretty useful. And like I said earlier, although this thing is now compiled inside a Docker image with GraalVM, this could be compiled to native image, and with native image, essentially it means that it's something that you can run without JVM on your edge, which is also interesting aspect. So now I'm going to move more from the software to backend. So what's happening with processing on the backend side. So the bird's eye view, the top view of the system is following. So you have this MQTT broker that essentially gets all the data from the edge devices, and then these events from this broker are then emitted to Kafka, and from Kafka you have two outputs. One is Influx Db, and the other is Neo4j. So Influx is essentially time series database, and Neo4j is a graph database, and this is essentially it from like top level. So these are the components that we have on the system. And on the right-hand side of the screen, that spiral, that's Grafana. It's a tool for visualizing stuff. So, but if you look a bit more closer to what's under the hood, it's something like this. So you have MQTT, and then you have MQTT source, which is a component that actually connects to the broker, reads stuff from it, and sends it to specific topics. And then you have, on the right-hand side, you have the two syncs. These syncs are essentially in reverse. So they read from topic to some kind of transformation or not. And then they store these events to Neo4j or Influx. Now, if you have more sophisticated processing where you want to either transform this data, or you want to reshape the data, or if you want to merge the data together, you need some kind of processing to happen. So you either build your own processing that will transform data from these topics, or you can use something like KSQLDB, which I'll talk a bit more in a while. And all here, what's in the pink color is essentially deployed to Kubernetes. It's part of Kafka Connect. What's in so KSQLDB here, it's also another service that runs in Kubernetes. What's in white is essentially in your Kafka. In my case, I'm using Confluent Cloud, which is essentially a cloud solution for running Kafka. So I'll talk a bit more what's in the Kafka Connect box. So Kafka Connect is essentially a framework, or you can see it as also as a service that you spin up either in your machine or in cluster or wherever you want, and you give it a definition, and that definition is then this either a sink or a source, and then it runs this thing. So it's essentially a program that will ship the data from one point to another, but it's usually built in a way that you don't have to deal with a lot of overhead that comes with writing software for Kafka itself. So this is one example of connector for Neo4j. So you see here that it's essentially a JSON file that you define. It's a definition. So you see on the top you have a sink definition. Here it's Neo4j sink. Then you need to give this sink information to how to access your Neo4j database. And then you need to define this topic that it's going to read from, and then you need to define a transformation in this case. So all the events that are coming through will be transformed to Cypher queries. So Cypher queries are queries that Graph database understands, and these queries will then result into nodes that are generated in the graph. And here you have a few other details. What's very interesting is the last line on this in this picture. So you can start connector from current state on your topic, or you can start the connector at the beginning of your topic. So that means that if you have, I don't know, millions of events, but you decide that from now on, we're gonna introduce, I don't know, Elasticsearch, you can say, I wanna have an Elasticsearch connector, and I want to import all the events from the beginning of our project. Or you can say, I want to ingest only the events that are coming from today on. So with this, you can essentially, with this powerful concept, you can always introduce new technologies, and you can reroll stuff if something breaks. This is really, really useful, not just for running stuff, but also for experimentation as well. Because, for example, if import fails, if you for some reason lose your Elasticsearch server or whatever happens, you can always recreate the connector and point it to a specific point in time, and it will regenerate essentially a state out of that. And because I said earlier, the Kafka has this ability to distribute events. Usually that means that your events are backed up correctly on various places, which means that all this stuff is really there to be really persistent. So this is then the example of few queries that are then generated and sent to Neo4j. I won't go that much into details, but yeah, this is then essentially part of the definition. And here you have another MQTT connector. In this case, it's a source. So here you have MQTT broker defined, some transformation, and then you define it where the events coming from MQTT will be written to. And as you can see, it's again pretty simple thing to define. So with that, I think you have a basic understanding what Connect platform for Kafka is, and how simple it is to operate. So like I said earlier, the other component that we need in our stack is then some kind of thing that you can use for doing this kind of transformations and manipulation of event. And that's where KSQL DB comes in pretty neatly. So KSQL DB is essentially a server. You connect it to your Kafka topic, and usually you also need the event schema registry. And it works essentially in a way that you define streams or views or materialized views or tables in it. And behind the scenes, this KSQL will run continuous queries that will generate a state, and that state will be then also stored in Kafka topics. So that means that you are consuming messages in Kafka, you're writing messages in Kafka, and if you need to get a state out of your system, you can also query KSQL DB. It's a very powerful addition to a streaming platform, and usually if you don't use something similar, you're gonna reinvent a lot. And I'm gonna go straight to a few more examples. So here is a stream that's defined in KSQL DB. This stream is reading from access points topic in Kafka, and it's transforming those events and flattening them. And it's also storing these events into another topic, but this time it's also defining a schema. So that means that all the data that's stored in this particular topic has a schema, which means that clients can also always subscribe to these topics, and they will understand the binary representation of the data. So this is very useful when you are storing data and you don't want to just send raw JSON. You want to be more, you need to understand what the data actually is in there. So this is like the basic case we have here. This itself is not that dramatic. You can achieve this kind of things if you build your own transformations on top of Kafka or whatnot. But it's a lot of boilerplate, and it's usually, as you can see, you can define this kind of stuff through SQL essentially. And that's not that impressive as to me as this thing. So here you have QSQL DB query, where you have two data streams coming in. One data stream is information about access points, and another is location of these access points. And these two data streams are coming at different phases. And you know, some devices do not have GPS device connected to it. And that means that GPS location is present, but not for all devices. Now, if you have a stream of location from some other device, what you can do is you can join this information together. So you have here a join query, a left join query, which is essentially a query that joins two data streams together and generates another query. So behind the scenes, there's going to be a continuous query that will join these two data sets together and generate another stream of data that could be used. So again, a very powerful solution. Okay, I'm gonna now go to visualization part. This is gonna be a bit quicker, I guess. So this is the one of the examples of how to consume the data. So here is another client that was built to visualize the data that's coming through the system. So you have here view of the access points feed, so you can see that in real time you're getting the access point information, so all the access points that were discovered. Here you have current view, which is essentially a state built on top of these events. And then you also have a third view, which is essentially events, raw events coming through these devices, and you can see them through this. Yeah, the pause button essentially just pauses the screen. And yeah, this is front end as well. And this is then the data visualized in Grafana from Influx. So what you see here, the pink color is essentially at the time where device was present, and the white is essentially when device was not present. And every small square on the screen represents 1 hour. So you can see I have two locations here and devices here. So you can see in some cases people are in with their devices, in some cases people are out. In some cases, you also have devices that are constantly connected, and they're also written here as well. And there's another chart here that shows this data also represented in a bit different way. So here you have all detected devices in a period of 5 working days. And the red stripes mean that there's working hours, so between 8 a.m. and 5 p.m. And the columns represent the number of devices that were detected at that time. So when you see the spike, that means that there's a lot of devices that are active during that hour, and then you see below when people are essentially sleeping or not present at that location. So you can see the influx of traffic coming in. So this is like stuff that you can do through time series database extracted from that data. And this is then the graph representation of the data that was extracted. So here I'm querying the access points information. So the access point I'm looking for is called gigatrons. I need to pause this one. So you can see here, you see two blue circles. They're essentially the same access point, but operating on different frequencies. And you can see here, when the stuff is exploded, the orange circles appear. Orange circles are essentially devices that are connected to these access points. The red lines represent probes that are being sent from one device to the access point. So that means that the device is trying to access that particular access point, and that probe was captured. And the green arrows actually mean that there is currently a connection being established between these nodes. There is another circle called gigatrons here that represents location. So these two access points were located at particular location. And now if I explore this location called gigatrons here, you're gonna see a bunch of access points that were detected on that. So these blue dots are actually access points that were found with monitoring this thing. Yeah. Okay. So I'm gonna go to conclusion now. So few bullet points. I wanted to demonstrate to you that event streaming is extremely powerful and extremely strong concept, and that it could significantly simplify a lot of your backend architecture. As you saw, a lot of this backend programming was essentially definition of sinks. So I didn't code transformation to get the data from Kafka to Influx. I didn't code the code to get the data from MQTT to Kafka. So, and the transformation that I did were very high level. So even the queries that you saw were not actually, I didn't write them in Scala or Python, whatever. It was all done through essentially defining SQL. I tried to demonstrate that Kafka is and should be considered as a strong backbone for your modern architecture. There are advantages that Kafka and brokers bring to the system. Connectors, once you have the Kafka up and running, are quite easy to scale up. I wanted to demonstrate to you that you can build these kind of agents and languages like Scala, for example, and that they can run on various different devices, as you saw. And with the help of Andraž, I also wanted to shed a light that this kind of monitoring exists because how wireless was designed, how wireless works. And that perhaps you could and should be more cautious when you're using your devices in open areas. If you want to protect yourself from a lot of this kind of monitoring, there are solutions that will randomize your MAC addresses, and a lot of this stuff is built on top of MAC addresses. You can also, hide your SSIDs on your home routers, or you shuffle them around to prevent this kind of things. And as Andraž also pointed out, there are other new standards that essentially encrypt these packets that make them harder to detect and harder to decipher. And the other good point here is that if you can't avoid using public Wi-Fi's. So for example, if somebody is doing this kind of research that I demonstrated here, if you then go in and you connect to their wireless public hotspot, and then you give them your email, then they will be able to link your MAC addresses, your device with your email, and that will significantly increase the value of the data that is possible to collect on you. So yeah, these are the key bullet points I want to get across.
Maybe just to add a few things. So basically, what Oto did, some of the vendors out there are already doing because of the censoring. If we're talking about security solutions, so sort of a protection of wireless LAN, and what is sort of a hype for the last few years is presence analytics. So big vendors has sort of solutions for presence analytics, and they collect those kind of data together with triangulation and so on. So figure out which devices are moving where and so on. So that is happening. Oto just took a DIY approach, but all the big vendors have, if not inbox solution, the cloud solution that does pretty much the same thing. So there's Kafka involved and everything in one cloud and analyzing the data in there.
Yeah, thanks, Andraž, for that addition. The other thing that you should take out of this is that, you know, when you make any kind of experimentation, when you play around with this stuff, you know, aim higher. You know, this could be quite boring. I could make, you know, just one device. I could just make this on my machine, but you know, we took it further and we learned a lot more out of it. And yeah, have some fun. You know, times are tough. Play around with this stuff and don't just work around. I want to thank at this point to everybody who helped. I want to thank Andraž. I want to thank Joško, obviously, and my family, and obviously all the friends and co-workers at Gigatronics. This kind of stuff is way more exciting if you guys are helping. Yeah, this is the QR code for the code base and the link to the GitHub repository. So everything that I've described and showed and demonstrated there is open source, and you can get Helm charts, you can get Kubernetes definitions. Everything is open source and you can use it. Yeah, I'm gonna blog about this stuff next year on my blog, so you can tune in and you'll be able to read more about this stuff on my blog once I write it down. And if you have any kind of questions regarding this, or if you want to have more private debate or whatever, this is my email. You can drop me a line and I'll try to answer it. And any kind of feedback is a good feedback. So thank you very much for that. Oh yeah, that's it. I'm done.
Okay, thank you very much, Oto and Andraž. This was a great talk, very detailed and well explained, I think. And I think it had many broader takeaways that are not, I think, stack specific, which is really nice. And I really like the part about event streaming architecture and state management. So yeah, it was awesome.
Thank you.
And we already have some questions. We already have a debate, actually. Okay, I'm just gonna read this. Oto, when working as a freelancer for a client, is event streaming the default when you're picking an architecture? When do you switch from PGSQL, MySQL to event sourcing?
Oh, that's a really, really nice question. usually I would advise that you first do at least 1 or 2 projects like this on your own, because otherwise it might be quite a dramatic shift for things that are you accustomed for. I think it comes out to that in the end. So what kind of team do you have available? Are they able to pick this kind of concepts? Are they able to make the change? The event streaming is also quite hefty investment in also Kafka and running Kafka. I would suggest, that means that, for example, for Postgres, you can just, start with one Django instance and then one Postgres instance, and you'll get really far with that. If you decide that you're gonna do stuff with Kafka, that means that you at least need to have 3 nodes to run this thing in production environment. So that means that you need to set that up, you need to run that thing, and then you need to scale it up. And that's completely new set of problems that you usually don't have the skills to manage. Now, it might sound scary, but the investment, I think, pays off still. There are now solutions like, for this case, I used Confluent Cloud, which is essentially a cloud solution that you just click through and you get Kafka environment production ready and ready to go, and you just essentially pay for the consumption and the traffic and the storage, and you don't have to deal with infrastructure, I would suggest. So, but you can start with event streaming without Kafka. You can start with CQRS. You can start with these kind of patterns. It just means that you have to change a bit how you think about designing for your domain. But yeah, I think it's definitely the future. But you need to read through the documentation from beginning to the end, because, for example, if you don't implement the state side of your event streaming thing correctly, or if you store events that you perhaps don't need, etc., you might have another set of problems that you are not familiar with. So I would suggest that you essentially start by reading through this thing. And I think, again, it's really powerful. It can help you solve a lot of problems, but it's definitely not for your small projects or anything like that. So that's my answer. I know it's not that helpful, but as usual with these things, it depends,
Okay, so another one was for Andraž, I guess, and there was a little bit of a debate about that in the chat. Can an iPhone or Android user randomize their MAC address? So
iOS for sure, Android, maybe people from Google can say something about it.
Someone said they both do.
Are you looking at the chat?
Yeah. It's a nice debate, I guess. So which MQTT broker have you used? That's what Oto, I guess.
Yeah, I played around with Mosquito, I think it's called. But the last stuff that you saw is essentially a public broker. So there are, I think, a couple of public brokers. I think Eclipse project has one. So if you want to play around with MQTT, you can use these kind of brokers that are either public, or you can use something like, I think it's called Mosquito, that you can set it up yourself. There are various commercial providers that will offer MQTT. I think Hive is one of them. And I also think that Confluent has its own variation of MQTT service. So instead of having your own broker, you can essentially kind of like have a service that directly emits data to Kafka. So it's essentially kind of like gateway. So there are various solutions. Like I said, in this case, I went with public broker. It was just easier to set up, and it's good for the job. If you follow this link, you'll see more documentation about, and you can see the examples, what was used and what was not. Yeah.
Okay. Why not Elasticsearch Elk Stack, since most of the Wi-Fi tools support JSON output?
That's a really good question. One of the key takeaways out of this talk should be that if you want to use whatever kind of storage or processing or whatever, you can. What you need to do is you just set up Elasticsearch and you create Elasticsearch connector, and you start shipping the emitting events from Kafka to Elasticsearch. And Elasticsearch will then index those events, and you can use whatever kind of tooling you have available or set up already. It should not be, the idea is not that you have to be opinionated what you use. If that's a better solution for your problem, then use that, connect it to Kafka, ship the data out, and you can use that. That's the idea.
Okay, so does Kafka keep full complete history of all events? And if not, what's the process of adding a new downstream database, such as Influx Db, Relax, Search?
Yeah. So Kafka stores has these consumer groups, and for every consumer group or for every client, it stores offset essentially, which means that it knows at what index out of the whole list of the events the client currently is. So you can again appoint consumer to whatever offset you want, or just the beginning or the end. So that's what you can use.
Clarify my question here. That means that Kafka still has all history of all the events forever, because you need to be able to reconstruct your downstream, right?
There are two things. Yeah, okay. There are two things. One is the offset. That's like separating. The other is then setting the policy of topic. You can say this this topic will have, I don't know, 5 gigs of messages. Once these size is reached, all messages will be deleted. Or you can have, I think it's called compact strategy, where all the events will be zipped or compressed, and then you can use them with some specific cases. You can essentially, the power comes from setting this up. So whatever you want, you can essentially configure this. So yeah, that's how you limit the stuff. So for example, when I have these events, and it's a lot of events, and I don't care about these events once I know that they're processed somewhere else. I set a cap to that topic to be 1 gigs, and that's the number of events that I need for my business case, and the rest can just go away. That's perfectly fine. You can also set, like I said, persistency on these topics, and these events will never go away. And then you can start thinking about Kafka more as a database than just a queue, I guess. Yeah.
Okay, thank you.